Hello, my name is Frank DiStassi, and today I'll be talking about how to generate bipolar voltage rails using a buck regulator or a Flybuck buck boost regulator. A little bit of a background on myself. I'm an applications engineer for Texas Instruments, and I've been working in power electronics for about 26 years now. So the first question we have to ask is, why do we need a negative rail? Well, many analog systems do require both a positive and a negative voltage. These include instrumentation and medical systems as well, and essentially they're used to power the op-amps. Another application for a negative rail would be a gallium nitride FET gate driver. Now, although the gallium nitride does not require a negative voltage, using a negative voltage to help turn off the FET improves the robustness of the gate driver itself. So today we'll be looking at two different ways to generate a negative rail. First, we'll look at what's called a polarity-inverting buck boost, or IBB. This particular solution is a very low component count solution, and it uses a standard buck converter to give you a negative output. The other solution we'll be looking at is a Flybuck or a Flybuck boost, and this has the advantage of inherently generating both a split positive and negative rail, and both voltage rails can actually track. So the agenda for the first part, we'll take a look at how to convert a buck into a buck boost, look at some design considerations, look at a design example, and then offer some reference material. So if we take a look on the left-hand side, we see an ordinary buck topology. It happens to be non-synchronous, but it can just as easily have been synchronous. On the right-hand side, we see a buck boost, in this case an inverting buck boost. And it's easy to tell that these are very similar. The input side is pretty much identical between these two topologies, and the only real difference is that the inductor and diode have been swapped. So essentially this gives us a clue as to how we can convert an ordinary buck into a buck boost. And we do that very simply by reassigning the input and outputs. The input voltage still goes to the same place as it did in an ordinary buck with respect to the system ground, but now the output voltage of the buck is actually grounded, and the common ground terminal for the buck regulator becomes our negative V out. And that's essentially all we need to do in terms of the mechanics of converting a buck regulator into a buck boost. So let's take a look at some of the design considerations we'll be going through here. We'll take a quick circuit analysis look, then we'll look at the voltage and current stresses on the components. We'll take a look at the maximum output current. We'll look at the right half plane 0 and the loop compensation. We'll consider the input-output cap, and then finally we'll take a look at some of the auxiliary functions that might be required in your application. So this slide shows a basic buck converter here in the center, configured as a negative output buck boost. Essentially, when the high side power switch turns on, the voltage across the inductor becomes equal to Vin, so energy is stored in that inductor. On the other half of the cycle, when the high side switch is off and the low side switch is turned on, the inductor is connected directly to the output voltage and ground, so the energy that was stored on that inductor gets dumped into the output cap and out to the load. Because the voltage has to flip across this inductor between the two half cycles, the positive output voltage, the positive input voltage that we established across the inductor becomes a negative output voltage in this buck boost configuration. A couple of things we should notice is that the input current here to our buck boost is a very discontinuous type of current with very fast rise and fall times. That's the same as it is for the buck. The voltage across the switch now swings from V in all the way to minus V out. So the magnitude of the voltage swing across the switch is much greater than it is for an equivalent buck regulator. The inductor current still has the same type of triangular shape as it does for a buck, and the average inductor current, as we'll see in a few moments, is quite a bit larger, in fact. So let's go into a little more detail of the circuit analysis. Essentially, the controller regulates the output voltage by adjusting the duty cycle of both the high side and the low side switches. If you take a look at the mathematics of this process, you'll arrive at the equation you see here on the slide relating the input to output voltage and the duty cycle. Now, one thing you want to be aware of for this type of inverting buck boost is that the output voltage can both be lower or higher than the input voltage depending on the duty cycle. That's a little more clearly shown in this graph on the right-hand side of the slide. At a duty cycle of 50%, the input voltages are equal, only the output voltage is now the negative of the input voltage. For duty cycles greater than 50%, the output voltage is greater than Vn, and for a duty cycle less than 50%, the output voltage is less than the input voltage. So essentially that's where the name buck boost comes from, because under one condition it is bucking the input voltage, and in another condition it's actually boosting the input voltage. So, as we mentioned earlier with the current waveforms, both the input and the output currents are chopped. They have a trapezoidal waveform. That means they have very fast rise and fall times, which in turn means that there will be more noise or input ripple than you would for a boost, and more noise or output ripple than you would have for a buck. So it tips us off that we may need to have a little larger output and input capacitors in order to help mitigate that noise. Let's take a look at the voltage stress across the buck regulator when it's being used as a buck boost. If you recall, a buck regulator, the voltage stress across the switches and from Vn to ground is only the magnitude of the input voltage when it's being used as a buck. However, when it's being used as a buck boost, that's not true anymore. So essentially we have to look at the voltage stress across all of the off devices. So at one part of the cycle the high side switch is turned off, and another part of the cycle the low side switch is turned off, and the buck regulator itself is connected between Vin and minus Vout, so we have to look at the stress between those two nodes as well. It's very straightforward actually. We can see here between Vn and ground is the maximum stress that the device will see, including these two switches. So that's simply equal to the input voltage plus the magnitude of the output voltage. You take a look at the example I have here on the right hand side of the slide. If my input voltage is 24 volts and I'm converting to a minus 15 volts out, that means the maximum voltage across those elements will be 39 volts. Basically, it means you can't use a regulator that has a maximum input voltage rating of only 36 volts for this particular example that we have in this particular application example here. Let's look at the current stresses now. Again, if you go through the careful analysis, what you will find is that the average inductor current in this equation here is equal to the output current plus this sort of correction factor, 1 plus Vout over Vn times the efficiency. For a buck regulator, the average inductor current is only the output current. So you can see that this term is always going to be greater than 1. So therefore, when you use a buck regulator as a buck boost, the average inductor current will always be greater than the output current, and it'll always be greater than an equivalent buck. Again, simple mathematical analysis, you arrive at the peak and valley currents using these two equations to calculate that. Let's take a look at our example here on the slide with a Vin of 12 volts, a Vout of minus 5 volts, an output current of 2 amps, 500 kilohertz switching frequency, a 10 microhenry inductor, and we assume an efficiency of 0.85. The average inductor current is 2.98 amps. That's quite a bit larger than our load current. If this had been a buck from 12 to 5, the average inductor current would have only been 2 amps. Here it's nearly 3 amps. And the peak currents are commensurately higher as well. So whatever buck regulator you choose to use in a buck boost application, make sure you compare these calculated current values with the current limits on the regulator to make sure that the regulator can provide your load current. So again, that brings us to the maximum output current, which is sort of just another way of saying the average inductor current. This equation allows you to calculate the maximum output current given the peak and valley current limits of your particular device. So let's take a look at another example. Basically, this is the same one as previously, 12 volts in minus 5 volts out. According to the data sheet of the LM4-3603, if you take the current limits and put them in these equations from that device, you get these maximum output currents from these two equations. Obviously, you have to pick the lower of the two, so under these particular conditions, if I were to use the LM4-3603, I could only get 2 amps maximum out of this regulator. Keep in mind that the LM4-3603 is actually a 3 amp buck regulator, so you can't get the full 3 amps out of it when you're using it as a buck boost. Let's take a look at power dissipation. On the left-hand side, we see that the conduction losses for a buck are proportional to the square of the output current, and the switching losses are proportional not only to the output current, but the input voltage and the switching frequency. On the right-hand side, we see that the conduction losses in a buck boost are proportional to the output current times this increase factor here squared. So again, as I mentioned before, this factor is always greater than 1, so the conduction losses will always be greater for a buck boost than for a buck. Same thing goes for the switching losses. Rather than V in, now we have V in plus the magnitude of V out, and the same increase in the output current factor in this equation. So again, the switching losses will always be greater for a buck boost than they are for a buck. And here we have an example just to kind of demonstrate how much more power dissipation there is for a buck boost. Let's assume that we're comparing a buck to a buck boost for the same type of regulator. All the resistance are equal, etc. 12 volts to 5 volts, 2 amps with an efficiency of 95%. That's very typical for some of our very high performance buck regulators. So the power loss for the buck would be about 0.53 watts. We go over here to this graph and we look at 12 volts in. We see that the ratio between the power loss of a buck and a buck boost is about 4. Multiplying that 0.53 by 4, we get 2.1 watts. Putting that loss back into the efficiency equation, we see our efficiency is now only 83% when I use that same regulator as a buck boost under these particular conditions. So be aware that your efficiency definitely will drop when you're using a buck regulator as a buck boost. The next aspect we'll look at is what's known as a right half plane zero. And this has to do with the small signal response of the control of the regulator. Now a buck regulator does not have a right half plane zero, but a buck boost or a boost, they both do have right half plane zeros in their control loops. A right half plane zero looks like a zero in its magnitude plot. So as frequency increases, the magnitude of the zero increases. However, the phase plot appears as if it were a pole. So as the frequency increases, the phase actually starts to lag, as you see here. This particular phenomenon depends only on the particular power stage, whether it's a boost or a buck boost, and doesn't depend on the control method, whether it's voltage mode or current mode. So in this slide we have a little, perhaps an easier way to demonstrate the origin of the right half plane zero. Let's suppose that the duty cycle increases very slightly in a transient fashion. Now ordinarily when the duty cycle increases for a buck regulator, the output voltage would tend to increase. But that doesn't happen for a buck boost. If the duty cycle increases slightly in a buck boost, the inductor is connected to the high side switch for a longer time than it was previously. The low side switch, therefore, is off for a longer amount of time, and therefore the output is actually disconnected from the inductor and from the input for a slightly longer amount of time when the duty cycle increases in a buck boost. Now, with the load isolated from the rest of the converter, the output capacitor has to supply the load. So if it has to supply the load for a slightly longer time during the cycle, the output voltage is naturally going to droop rather than increase. But on the other hand, since we are turning on the high side switch for a slightly longer time during the cycle, it means we're storing more energy in the inductor, even though less of it gets through to the load because the low side switch is not on as long as it was. So therefore, eventually, since we are storing more energy into the inductor, the output voltage will recover and start to increase as it should, or as we would have expected if this had been a buck regulator. So essentially, if we look at it in a time domain transient, suppose the duty cycle is running here at 50% and all of a sudden we increase it to 75%. In a buck regulator, we would expect this output voltage to climb and then reach a new steady state value. Here, in a buck boost, the output voltage actually falls first and then increases to its new steady state value. This actually has the effect of causing sort of a reversal in the feedback loop phase of your regulator. In other words, the controller increases the duty cycle expecting the output voltage to go up and close the loop using negative feedback. In this case, momentarily, that negative feedback actually changes to positive feedback during this transient, and therefore it can have an adverse effect on your control loop. So let's take a look a little more closely at this. The formula for calculating the right half plane zero, which we saw a couple of slides ago, I reproduced it here. It's not too difficult to calculate. It depends on quite a few things. It depends on the input and output voltage, the value of your inductor, and the output current. So, as an example, for 12 volts in minus 5 volts out, an 8 microhenry inductor and 2 amps out, the frequency of the right half plane zero is approximately 84 kilohertz. Now, that, again, since it is a right half plane zero, it adds quite a bit of phase lag rather than phase lead. So what you want to be sure is that the overall loop gain of your system crosses over at a much smaller frequency than what you calculated here. Typically, we recommend it should be at least 1/4 of that frequency. So in this case, you should try to design your control loop so that the crossover frequency for the loop gain is somewhere in the 20 kilohertz region. If you look at this equation, we can see what affects the value of the right half plane zero. Of course, the worst case is the lowest frequency, because you don't want to have to limit your bandwidth any more than you have to. So low input voltage and high output voltage conspire to give you a low frequency for your zero, and a larger output current and larger inductance also conspire to give you a lower frequency. So in this equation, we can see that the inductor is probably about the only handle or knob that you have to turn in order to adjust this frequency at least to some extent. The other thing we should mention is that there are two different control methods with any regulator, and that is voltage mode or current mode. And we recommend that if you're going to take a buck regulator and use it as a buck boost, we recommend that you use a current mode type regulator. The single pole response is much easier to compensate in that case. The double pole existing in a voltage mode type control only compounds the difficulty that you'll have with the right half plane zero when you try to compensate the loop. Of course, if possible, you should try to select a regulator that has external compensation components to give you much more flexibility when setting your loop characteristics. A couple of other things that you can do to help mitigate the right half plane zero and just compensate in general. As I mentioned, the inductance gives you some degree of freedom. However, you have to be aware that the value of the power inductance affects the ripple which affects your efficiency and some of your other parameters as well. So you don't have a lot of variability there. Again, externally compensated regulators are much easier to tailor the frequency response. So that's one option. Another option is to use a feed-forward capacitor. Again, you have to be a little bit careful because the feed-forward capacitor gives you a pole and a zero, but in some cases it might be able to give you just enough phase boost to give you good performance. Finally, increasing the output capacitor over where you would normally set it for a buck regulator is another good way to limit your control loop bandwidth and help mitigate any issues with the right half plane zero. So let's take a look at the input and output capacitors associated with a buck boost. We can see here on the left-hand side that the ordinary input capacitor for the buck, which goes between Vn and ground, now becomes our input-output cap for the buck boost, and it's important to have that cap. It's easy also to see that the output capacitor for the buck is exactly the same as it is for the buck boost. It's in the same location. One thing we do need is a new true input capacitor which goes between Vn and the system ground of the entire system to provide some transient currents to the input to the buck boost regulator. So this is the only capacitor that needs to be added. Now the three input capacitors Cin, Cio, and Cout have a tendency to share the high frequency ripple currents. That means that in some cases you might be able to reduce their values and get the same ripple current. CIO can help with low transients. Essentially what it does is it helps to provide another path for the output low transient current directly from the input, so the regulator doesn't have to respond as quickly. You can pull the load current directly from the input of the regulator. Typically, the I/O should be sized at least as large as your output capacitor, and it certainly can be increased if needed. These capacitor values typically will be selected empirically, however. All right, let's take a look at the auxiliary functions. Since the ground of the buck now becomes the negative output voltage, we're going to need some kind of level shifting if we want to access some of these features of the buck regulator, which are all referenced to the buck regulator ground itself. So we'll take a look at enable, clock sync, power good, miscellaneous controls, and we'll take a look at adjustable output voltage. All right, the enable is the first thing we'll look at. We see two different methods here. The one on the left is very simple. It uses a single PNP transistor and some resistors in order to level shift your logic-based or ground-based, system ground-based enable to get it into the buck regulator. This particular solution requires some current from your logic, and it has a great deal of hysteresis, but it is very simple. Here we have two extra transistors, or one extra transistor added, so we have a total of two. In this case, the enable threshold is simply the threshold voltage of this FET right here, and there's no real hysteresis. And of course, it doesn't require any current from your logic supply. In both cases, you have to make very sure that you always respect the ABS max rating between the enable input and the ground of the particular regulator that you're using as your buck boost. Another issue sometimes becomes input UVLO. The simple circuit that you see here can be used to activate the enable input of your buck boost based on the certain thresholds on the input voltage. And it's very straightforward to design the threshold that you need from your input, and also to get the hysteresis. Here we see two different methods to apply frequency synchronization from an external clock. In the lower left-hand corner, we see a very simple method here, a simple RC with a diode clamp, And as long as you keep the RC product much greater than 1 over the switching frequency, this little system right here is a pretty simple and easy way to synchronize your buck boost. Up on the right-hand corner here, we see a little more sophisticated type of sync feature. This is a little more gives you a little higher performance for some of the very high frequencies, as long as you are careful with your selection of your components. The power good flag may also need to be level shifted if your application requires that. Again, here on the left hand side we see a very simple structure, 2 resistors and a diode. Really the only disadvantage to this particular structure is that your power good, instead of going to ground, will actually go slightly below ground by a diode drop. But if your logic circuitry that's using this power good flag doesn't mind that, then this particular setup is actually quite good. So this power good signal will swing from V logic down to about a diode below ground. If you can't afford to have your power good swing below ground, then the circuit you see here on the right hand side also works very well. So again, the power good would swing from your external logic supply all the way to ground. Again, for both of these, make sure that the ABS max on the power good pin between power good and ground is not violated in any of these setups. In this setup, power good will see V logic plus the magnitude of V out. In this setup, it only sees the magnitude of V out. Again, oftentimes you might need an output voltage clamp. As an example, if the CIO, the input-output capacitor, is connected directly between VIN and V out. If VIN should rise suddenly, then CIO will couple a positive voltage to your negative output, and that might disrupt some of the op-amps or some of the loads that are sensitive to a positive voltage when they're expecting a negative voltage. The other issue sometimes is that if you're using a split rail, both a positive and a negative supply, such as for an op-amp, the op-amp is seen as a common load between those positive and negative supplies. And if the positive supply starts up before the negative does, then the positive supply might try to force the negative supply positive. So again, the clamp will protect in that case and make sure that the negative output doesn't go more positive than a diode drop. Alright, so let's look at a design example. Here we'll use the LM73605 buck regulator as an inverting buck boost. This is one of our latest synchronous buck converters. So our design inputs will be a VIN of 12 volts, an output voltage of -5 volts, and an output current of 3 amps, and a switching frequency of 500 kilohertz. Let's take a look at the voltage stress. Well, 12 volts plus 5 volts is only 17 volts, and since this device is rated for 36 volts, there's no problem there. Let's also calculate the duty cycle and the on time required for this application. We use these two equations to do that. In this case, the duty cycle is 0.29, and the on time is 580 nanoseconds. If you take a look at the datasheet for the LM73605, we see that these are well within the limits of that particular device. Furthermore, this should be checked both at the minimum and maximum of your input voltage range. So we need to calculate the inductance also. For a buck boost, you can calculate the inductance pretty much the same way as you do for a buck. The equation is shown here on the right hand side of the slide. Typically we pick a ripple current of about 30% of the maximum load current. So in this case, 30% of 3 amps is 0.9 amps. Call it 1 amp. We calculate a 6.9 microhenry inductor, so we'll pick a standard value of 8 microhenries in this particular case. Now we got to take a look at the currents. Let us assume an efficiency of 85% when in the buck boost mode, and the delta IL we just calculated is 0.87. We'll use these two equations in conjunction with the peak and valley currents from the datasheet to calculate what our maximum output current could be. So here's the datasheet for the LM73605, the part that pertains to the current limits. Using the 6 amp minimum of 6 amp high side current limit, we get 3.7 amps from this equation. Using the minimum of the low side of 4.79, we get 3.5 amps. So we can see that this device will be able to supply our load current of 3 amps. Keep in mind that this is actually a 5 amp buck regulator, and we can only get a little over 3 amps out of it when we're using it as a buck boost. We also need to know the average inductor current, and it's good to know the average input current as well. This equation is used to calculate the average inductor current based on the values that we already know in our application, and we come up with about 4.5 amps. The average input current for the given conditions will be about 1.5 amps. Let's check the efficiency and the power loss. From the data sheet, as a buck, going from 12 to 5 and 3 amps, the efficiency is about 95%. That gives us a loss of almost 0.8 watts. Again, if we go back and to a few slides past, we'll see that the relationship between the power loss of a buck and a buck boost under these conditions is about 4x. Multiplying 4 by 0.79, we get about 3.2 watts. Putting it back in the efficiency calculator, we get about an efficiency of 83%. So again, it's quite a bit less, but that's what you can, about typically of what you can expect when using a buck as a buck boost. So the inductor has to be an 8 microhenry inductor rated for at least 5 amps, and be sure that the inductor you select doesn't saturate at the peak current limit of the LM73605. And of course, you need to follow all the datasheet recommendations, as you all normally would. Let's check the right half plane zero frequency. For the conditions that we stated in this example, the right half plane frequency is about 56 kilohertz. So we want to make sure that the loop crossover for the LM73605 is somewhere between 20 and 30 kilohertz. This particular device has internal compensation, so there's not a whole lot we can do. Probably the best thing we can do is make sure we use a large enough output capacitor so that the bandwidth is somewhat reduced. In some cases, we can also use a feed-forward capacitor, as I mentioned earlier. So let's take a look at the input and output caps that we can use for the buck boost. The datasheet recommends at least 88 microfarads for the same buck application. So we may need a little bit more than that for the buck boost, but that's a good starting point. So we'll start with 4 by 22 microfarad caps for our output cap. The input-output cap should be approximately the same, essentially, as the input cap. So in this case, we'll use one 22 microfarad for our CIO, and we'll use one 22 microfarad for our actual CN. And that's will get us a stable regulator, and that's a pretty good starting point. The feedback divider that we use to set the output voltage is exactly the same as it is for a buck. So here's the complete solution. LM73605 configured as a buck boost. The ground and all the other systems, all the system ground here, now becomes R minus V out. What used to be the output of the buck is the system ground, and our input stays the same between here and the system ground. 8 microhenry inductor, feedback divider, output capacitor, input-output cap, and the main actual input capacitor. Of course, like any regulator, you still need the CVCC, the C-bias, and the C-boot as you would for any buck regulator. So, to finish off this first section, I offer a few reference designs. In fact, we have quite a few reference designs that demonstrate how to take some of our very high-performance buck regulators and use them as buck boost regulators, not only to get negative output voltages, but actually to get plus or minus split rail voltages as well. All right, for the second half of the presentation, we'll take a look at generating a bipolar voltage rail using a Flybuck or a Flybuck boost converter. First, we'll take a look at the Flybuck and Flybuck operation design. Secondly, we'll take a look at the Flybuck boost operation and Flybuck boost design. And finally, we'll take a look at some layout and troubleshooting hints. Basically, we see here the basic Flybuck converter. Essentially, to make a Flybuck, you take an ordinary buck converter and replace the inductance with a transformer. During this part of the cycle, Q1 is turned on and Q2 is turned off. The voltage across the inductor is Vin minus Vout. Under these conditions, the polarity is such that the output diode is turned off. So the load current on the secondary side is supplied by the output capacitor. The next part of the cycle, transistor Q1 is turned off and Q2 is turned on. In this case, the voltage across the inductor is equal to the output voltage. The polarity is such now that the output diode is turned on, so the secondary output current can flow through the secondary winding. It gets reflected to the primary winding, so now the primary winding has the sum of both the primary load current and the secondary load current at the same time. And these add together to essentially give you a triangular current waveform. Now, this slide shows all of the parasitic resistance and inductances of the transformer, and these essentially are what's responsible for degrading your load regulation. In this case, we see an example where the secondary load current is very large, but the primary load current is very small. In this case, your secondary output voltage will be somewhat lower than designed, due to all of these voltage drops the way they add and subtract. The equation at the bottom of the slide indicates how you can estimate what your output voltage will be under these conditions. The other thing to notice is that the leakage inductance of this transformer will cause a very large distortion in the current on the primary side. It'll cause it to look quite a bit different than that for an ordinary buck regulator. In this case, we look at the opposite example, where the load current in the secondary is very light and the load current in the primary side is very heavy. In this case, the voltage drops add up such that your secondary output voltage will be larger than desired. In this case, you can either use a preload or a Zener diode as a regulator. Let's take a look at the control method that we can use for a Flybuck type topology. Essentially, the constant on-time control is well suited for a Flybuck type of topology. And a constant on-time is essentially a ripple type regulator, where the output voltage ripple is being controlled and regulated. Let's say that the output voltage is falling, and when it reaches the reference voltage at this point, a one-shot timer is triggered off. When the one-shot timer is triggered, the high side switch is turned on, connecting one side of the inductor to Vin, storing energy and sending current to the output. Under that condition, the output voltage will start to rise. Once the one-shot has timed out, the high side switch is turned off and the low side switch is turned on. And under those conditions, the output voltage will start to fall again. As soon as it reaches the regulation point, the one-shot will be triggered again and the whole cycle will be repeated. The duration of the one-shot on time can be made to adjust with the input voltage in order to make the frequency of the constant on-time control a little bit more constant. So essentially this is a ripple type regulator. So since the control does depend on the ripple, we should take a little closer look at the ripple on the output voltage. Essentially, if you use a output capacitor that has a very low ESR, such as a ceramic capacitor, the voltage across this capacitor will tend to be 90 degrees out of phase with the inductor current that's feeding into that capacitor. Unfortunately, this has a rather bad effect on the stability of the constant on-time control method. Essentially, to get good stability, you want the ripple voltage to be more or less in phase with the inductor current ripple. We see here an example of a stable constant on-time regulator and an unstable constant on-time regulator. Essentially, in this case here, you see that the duty cycle is well controlled and the frequency will change depending on the input and output and load. On this side here, we see that the inductor current is rather jagged and we can see multiple switching action occurring here and here. If you see this kind of waveform in your application, then you know that your constant on-time regulator is unstable. So how do we prevent this kind of instability with our constant on-time control? Well, the most obvious way to control that would be to add external ESR to your output capacitor. This is kind of a brute force method, and it's not very good for some obvious reasons. So typically this type of correction is not used. Or we could add some ESR in series with the inductor. Again, this has the result of reducing your efficiency and is very rarely used as a mitigation. However, type 2 and type 3 that we show in the center of the slide here, these are actually very good ways to help create the proper feedback ripple for our constant on-time controller. Type 2, we simply have a feed-forward capacitor across the topside resistor feeding directly into the feedback. With type 3, we have this RC network that tends to look at the voltage across the inductor and tries to extract the inductor current information. Then this cap takes that inductor current information and injects it into the feedback. Both of these methods will help to get a ripple feedback that is more in phase with the inductor current. The equations we see at the bottom of the page will help you select the proper components for either of these two methods. So let's go a little more deeply here. We see that R sub R and C sub R in the type 3 compensation generate a voltage that reflects the inductor current, basically. Then CAC couples that current or voltage signature into the feedback pin. So it's pretty much essential for good performance of a constant on-time controller to have your ripple voltage in phase with the inductor current. One more thing that you should keep in mind is that with this kind of an architecture, the average output voltage will be slightly more than the reference voltage by approximately half the ripple. Here we have the key design equations for a Flybuck design. Essentially, you want to select your output voltage, calculate your turns ratio, take a look at the diode rating, calculate your primary inductance, and check your peak inductor current, and then select your C out for your primary and secondary side. So these equations are pretty much very straightforward. TI also has a quick start calculator that is keyed to the LM5160 Flybuck regulator. Should anyone be interested in taking a look at those calculators, I encourage them to go to ti.com. So let's take a look at some of the specific features that would be required of a buck regulator in order to achieve good performance in a Flybuck application. First of all, you want to choose a synchronous type converter. The synchronous converter allows the inductor current to become negative and is very helpful in achieving very good load regulation all the way down to no load. Converters that have a valley current limit are probably not as useful as otherwise in a Flybuck application. In order to use a converter with a valley current limit, it requires to have some kind of an off-time control during the current limit event. Now, TI has several regulators that are specifically designed for Flybuck applications and that have all of these features you see on this slide built in. One such family is the LM5017, the 5018, and the 5019, and another example is the LM5160 and 5161. The other way to generate bipolar voltage rails is to use what we call a Flybuck boost converter. In the Flybuck boost converter, the advantage is that the transfer function between the input and output is related to d over 1 minus d, as you see here in this slide. What that means is you can get twice the output voltage for a given duty cycle, and this makes low input voltage operation very attractive. So here we see the basic Flybuck boost topology. Essentially, what we have is the inverting buck-boost regulator that we saw earlier, with the inductor replaced by a transformer. So during the first half of the cycle, Q1 is turned on and Q2 is turned off. In this case, the voltage across the inductor is just Vin. The polarity is such that the diode in the secondary side is turned off. So the secondary load current is supplied by Cout, and the primary load current is also supplied by its Cout during that time. During the next part of the cycle, transistor Q1 is turned off and transistor Q2 is turned on. In this case, the voltage across the inductor is equal to the minus Vout of the primary. Also, the polarities are such that the diode is turned on in the secondary side. So there is secondary side load current flows through the secondary and is reflected into the primary. So the primary now sees both the primary load current and the reflected secondary load current. So it's larger than the what you'd have in an ordinary buck or an ordinary buck boost. So essentially the design equations will be the same for a buck boost in combination with a transformer type secondary output. So there's some advantages and disadvantages with a Flybuck boost. As mentioned, in a Flybuck boost, you have a lower duty cycle than in a Flybuck for the same input and output situation. The transformer secondary to primary turns ratio can be lower. Basically, this means you'll have fewer windings on the transformer, which may make it a little bit smaller. It also means you'll have lower leakage inductance and DC resistance, and you'll have less current ringing caused by the transformer parasitics. So all this adds up to meaning you'll have improved load regulation with a transformer with a smaller turns ratio. On the downside, essentially we have the same issues as with an inverting buck boost. Essentially the inductor current in the Flybuck boost is higher than it is for a buck or a Flybuck. And again, the maximum voltage that the converter will see across its terminals will be the input voltage plus the magnitude of the primary voltage. So essentially we see here on the top a Flybuck boost and on the bottom a Flybuck using the LM5017. It's easy to see that this stage here, the LM5017 stage, is nothing more than the same inverting buck boost that we saw previously, and here we've replaced the inductor with a transformer to get our secondary output. So in this case here, we'll have our negative output coming at this node, and this node can be used either as positive or a negative output. The Flybuck down here, again, is just a simple buck regulator, all ground referenced, where the output voltage will be positive and the secondary voltage can either be positive or negative in this case. As we mentioned before, for an inverting buck boost, the duty cycle is much less over a very wide range of input voltages than it is for an ordinary buck. Here we have the design equations for the Flybuck boost. Essentially, again, you select your Vout1 and Vout2 on your primary and secondary. Select your frequency, since this is a constant on time, so the frequency will change somewhat with Vn perhaps, and duty cycle. Check your inductor currents, calculate your primary inductance, check your peak inductor current, and double check your input voltage range. Now the secondary winding will have to be either somehow regulated or used as your output in a split rail design as we see here. And the simplest way to do that, either with a Flybuck or a Flybuck boost, is to simply use a transformer that has a center tap. Well, this is very simple, but it's also very low performance. The cross regulation between these two outputs is rather poor. Also, you need a transformer with more windings, essentially, so it may end up being larger and it may have more parasitics. The next step would be to use a transformer with only one secondary and use a Zener diode to regulate at least one side of this output voltage. In this case you get a little bit better regulation, but you still have rather poor cross regulation when the two loads are different. Finally, we come to a little bit better solution, probably the best solution that you can have. Again, a transformer with a single secondary winding, a reference voltage here that very accurately regulates the voltage between these two nodes, and an op-amp and a buffer that generates a virtual ground at this point. So the buffer can both source and sink current coming from your load, and this reference voltage is able to very, very accurately control the voltage across this node here. So this is probably the best way if you need a good split supply. Let's take a look at a Flybuck boost example. So we have our input voltage of 15 volts, an output voltage of plus or minus 12 volts, and an output current of plus or minus 400 milliamps. Our targets will be to have a 1 minus D duty cycle greater than 0.5, only use 2 windings, a low turns ratio, and we'll try to get the peak currents down to be as low as possible. So let's take a look at some of the considerations we have. Let's suppose that we set our Vout primary to 7.5 volts. Well, that's not really related to 12 volts at all. That means if we did that, we would require a transformer that had 3 windings and a step-up ratio in order to get our 12 volts out. So that's rather a poor solution. Or we could set our primary to 12 volts, a positive 12 volts, which is what we would do if we had a Flybuck. In this situation, the 1 minus D is much, much less than 0.5, and that'll lead to a poor regulation. Finally, however, if we set our primary output to be minus 12 volts using a Flybuck boost, then we can use a transformer with a 1-to-1 turns ratio and get a positive 12 volts out, which is what our requirements are. So that's the best solution. Here we see some more calculations based on this spreadsheet. Again, based on the LM5160. In this spreadsheet, we calculate the power dissipation and some of the peak currents, which are all required before we can commit to a final design. And again, this calculator is available from Texas Instruments for anyone who's interested. Now, of course, a Flybuck or a Flybuck boost requires a transformer. And sometimes designing transformers can be a little bit intimidating, but that's okay because nowadays we have a lot of companies out there who will design our transformers for us. So all we need to do is bring the correct specifications to the transformer manufacturer, and he will take care of the design of the transformer for us. In this case, we want to make sure that we tell the transformer vendor that we need a gap in our core. The other specifications that we need to provide are the peak current, the switching frequency, the primary inductance that we require, the target leakage inductance, which should be less than 1% of the primary inductance, and any kind of isolation or size requirements that we may need for our application. Once you give those specifications to the transformer vendor, he may actually have a transformer off the shelf that can be used in your application. Another important issue with either a Flybuck or a Flybuck boost is the diode that you use in the secondary of the converter transformer. Essentially, we recommend that you use a Schottky diode. This has almost no reverse recovery issues with it, and therefore the load regulation will be much better. With an ultra-fast diode, you not only have a large reverse recovery peak, but you also have a large reverse recovery time. And that current will interact with the leakage inductance and the other parasitics of the transformer to degrade your load regulation. So essentially, we recommend using a Schottky diode, and find a diode with the lowest possible voltage, forward voltage drop also will help to improve your load regulation. So we definitely have to provide feedback to our converter. If we have a split rail using a Flybuck boost, in the previous example of plus or minus 12 volts out, all we need to do really is to connect our two feedback dividers here, the two resistors, one to the positive output, one to the negative output, and the center tap going to the feedback pin. This provides a easy way to regulate between the two output voltages. Unfortunately, it is non-isolated. Now, layout, of course, is a very important concern for any type of switching regulator, whether it's a buck or boost or Flybuck or anything else. This slide shows some of the most important considerations for any kind of a switching regulator. First, make sure that your input capacitor is very close to the power and input pins of the IC. Some of the auxiliary components, such as soft start and the R-on resistor, in this case for the LM5160, should also be placed physically very close to the IC. Again, the feedback divider, the top and bottom, and any feed-forward capacitor that you might be using also need to be physically close to the feedback pin and preferably to an analog ground on the IC, near the IC. Most regulators have a VCC capacitor, which provides a stable capacitance to the internal LDO of the device. This capacitor should be physically close to the VCC pin, with its ground having vias down to the ground plane. Again, most converters require a bootstrap capacitor, which also needs to be physically close to the regulator, and so that it can be connected to the switch and boot pin with very short and wide traces. If we're looking at a Flybuck or Flybuck boost that has a transformer, we want to make sure that the loop area here on the secondary of the transformer is kept very small, which means keep the diode and the output capacitor close to the secondary. If we're doing this type of Type 3 feedback, let's say with the LM5160, these feedback components should be very close to the primary of the transformer, again keeping this loop area, the current loop area, very small. Then you can take the feedback differentially from this capacitor and feed it back to Vout, or feed it back to the feedback. So here we have a very short list of some troubleshooting hints, or at least to make your first design go a little bit easier. Of course, you want to make sure that your design parameters don't violate any of the specifications, whether of your application or the IC, and check the datasheet very carefully to make sure you're not violating any datasheet specifications. Check your component selection, just double check to make sure you have the right values. Double check your ripple injection method, how you're doing that, and also be sure that your inductor or transformer won't saturate under the maximum peak current that the converter is capable of producing. And finally, of course, check your layout. So here we have a few tips of what to do when some of the most common issues might come up with your regulator. With a constant on-time regulator, instability is probably one of the most common issues that you'll see in steady state. And the most common problem, the most common reason for that problem is that your ripple injection components have not been selected correctly. So if you see any kind of instability with a constant on-time architecture, double check your ripple injection methodology and your component values. The other most common issue we see with a secondary type of output converters, as we have here with our transformer on the secondary output, is load regulation issues. And many times the output voltage will be a little bit too high than we designed, and typically we can either use a Zener diode or a preload resistor to help bring that down a little bit. Other issues might be the reverse recovery time of your diode if you're not using a Schottky. And of course the forward voltage drop across your diode, regardless of what kind of diode it is, will affect your load regulation. So those are points to look at if you see issues with load regulation. Pre-bias startup sometimes we also see, especially if you have an input voltage that is, or an input voltage supply that is somewhat weak, and as the converter starts up it might tend to draw the input voltage down. So in those cases using a little bit larger input capacitor can help. And again, sometimes you'll see large inrush currents during startup, and sometimes this can have an adverse effect on your input voltage supply. So in this case, you might need to use a little longer startup time by increasing the soft start capacitor on the regulator. Low transient perturbations are another issue that are seen quite often. Sometimes your low transients are a little bit larger than you would like them to be. And really, in this case, the best way to mitigate that is to increase your output capacitance. Finally, many times we find that the application or the converter can't supply as much load current as we thought it should. And typically what that means is that we've somehow miscalculated how much peak current we need for the application, and the current limit on the regulator is limiting how much current we can get out. So we may have to choose a different regulator, or perhaps choose a different inductor to get different peak currents. Finally, we have quite a few tools and resources at Texas Instruments in order to help our customers design Flybuck and Flybuck boost applications. You can see here that, as I mentioned before, the LM5017 and 5160 family of devices are specifically meant for Flybuck and Flybuck boost, and we have quite a few app notes and design tools available to our customers. So I encourage everyone to check that out at ti.com. And that's the end of our presentation, and thank you for listening.